intense heating and by the equator, close to the equator, there tends to be a surplus of heat that's actually input or put in or introduced into the surface of the planet. On the other hand, past 45 degrees north and south in the upper latitudes, there tends to be a deficit. That is, more heat is actually lost than gained on the surfaces, and this is where you usually have a net loss of heat. So there is this tendency for heat that's actually accumulated right here close to the lower latitudes and also in the equator to be transported towards the poles, and that's done, as we said, by air masses as well as by current masses. How this, if it in a very, very simple world, if the world was not, or the Earth was not rotating, that would have been a very, very a simple continuous flow. Something from the equator here, air rising from the equator because it's warm, and then it moves polewards, northwards or southward. And then where it's coolest, it would have sunk down. So you'd have one big circulation cell in the northern hemisphere and one big circulation cell in the southern hemisphere, both of course rising at the equator and then sinking in the poles. However, because we have a rotating Earth scenario, what happens is it's slightly complicated. So let's just review this again. Heated air masses rise and flow poleward, and then the poles, air masses would go and sink and float back towards the equator. That would be the tendency of these air masses to do so. And this is what we would call a convection cell. But as we said, because of the Earth's rotation, these convection cells are further divided. Instead of just having one in each of the hemisphere, you'll end up having actually about 3. Let me explain how that works out. Part of the reason why this happens is because of what we call the Coriolis effect. The Coriolis effect is simply the deflection of any fluid that may be moving over the surface of the Earth. The surface of the Earth, of course, being curved and also rotating, causes the relative motion of the path of that mass of air or mass of current to be deflected. What causes this is the fact that the curved Earth has different rates of rotation. The rotation of the Earth right close to the equator tends to be a much faster speed, because the Earth, of course, is its widest at the equator, and so within 24 hours its rotation covers a much longer distance. On the other hand, places at the pole tend to go and have slower rotation because they tend to go and cover a much smaller distance as the Earth actually rotates within 24 hours. So points closer to the equator tend to go have faster, what we call eastward rotational velocity. Eastward because remember that the Earth rotates from west to east. That's the reason why the sun rises at the east. Because our relative motion towards it is actually west to east. And the velocity of the rotation of the Earth, as we said, closer to the poles, much shorter. So in the northern hemisphere, here's what happens. Let's say we have an object that is actually traveling from the equator toward the pole, towards the North Pole. As it leaves the equator, and again assuming that this is a fairly fluid material, for example air masses or water masses, they're not subject to any kind of drag from the surface of the Earth as it actually is moving. What is traveling towards the pole from the equator, it is taking on the initial rotational speed from its origin, which is the equator, and as it travels northward or poleward, it is going over surfaces that have slower and slower rotational speed. So instead of apparently going straight up north, it would go and start moving a little bit ahead of the rotation of the other of the places beneath it, and so it seems to be veering to the right. So it starts out with a fast rotational velocity, because it's at the closest to the equator, and as it moves over the higher latitudes, say, for example, going to 30 degrees north, or 40 degrees north of the equator, it starts to move ahead of the Earth's rotation because of its initial velocity is much faster coming in from the equator. When that happens, if you are actually observing this object from its point of origin, and you have a really strong, powerful telescope, or you're observing this whole phenomenon from space, from a satellite, what you see is that as it actually moves from the equator toward the pole, is that it seems to be veering to the right of its intended path. This actually applies also to planes that are flying, across long distances, across continents and so forth. Every time they go and take off, they have to adjust their position and their location due to the Coriolis effect. Okay, so if they were just going to go straight, take a straight path as they fly over the rotating Earth, okay, they would actually look like they're actually veering to the right as they're actually traveling in a northern hemisphere. Now, what if it actually moved? It was flying or moving from the pole towards the equator. Would we still see the same phenomenon? Well, yeah, you also will, because of a very similar set of reasoning. You start off, let's say we're coming in from the North Pole, higher latitudes, and we'll be flying a plane or riding a strong wind with a kite, okay, heading towards the equator. We start off at higher latitudes with very slow rotational speed. So we start with that. Okay, now remember, as we're moving down south, okay, our rotational speed is again heading towards the east. Okay, it's an eastward rotation. When we approach, towards the lower latitudes, it would tend to go and lag behind the Earth's rotation, because as we go towards the lower latitudes, the rotational speed beneath us, or beneath that object, is actually moving faster and faster. So what happens is that if we have somebody observing this from the point of origin, or again from a satellite above it, the object seems to go and again still veer to the right, okay, just as before. Okay, so the Coriolis deflection in the northern hemisphere tends to go and actually deflect paths of any object moving in a fluid motion with very little friction. Think of air currents, think of planes, think of long-range ballistic missiles, think of surface water currents, etc. They always tend to go and veer to the right from their point of origin because of the Coriolis deflection, which is due to the Earth's rotation. On the other hand, you follow the same kind of reasoning in the southern hemisphere, and what we'll see is that the deflection of the Coriolis is actually to the left. Okay.
Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.